Hey folks, this is Major Jones here to talk to you about finite state machines. We're going to build off of what we did last time in the last lesson where we talked about how to actually sort of build a circuit to implement this device. And today we're going to look at a couple of new integrated circuits that'll make building these finite state machines much easier. Okay, so recall from, let's see if I can pull this up, our last lesson, right? We worked all the way through to this circuit right here where, at least in simulation, right, we can throw down as many logic gates as we want, plug that into some flip-flops that represent our state bits, and build our finite state machine. Something this small, you can imagine building out of the logic gates we used so far in lab, and it wouldn't be too difficult. Right, so here's kind of like the general graph or diagram of our finite state machine. So in our lab on counters, we saw the 7474, which was an integrated circuit that had 2 D flip-flops in it. That's totally sufficient to build like a small finite state machine. And as long as we don't have too many different logic gates, then out of a couple of 7408s or 7432s, we could build the combinational logic to compute the outputs or the next states, and that's one solution. It's not that bad, but if we have many state bits, or if we have many inputs or many outputs, right, then that starts to get a little unwieldy. So today we're going to look at what are our options. Right, we've identified at least one to hold our state bits to 7474. We will use one more, the 74175. Which actually maybe I'm forgetting right now if we use that in the lab. But this is another integrated circuit that now has 4 D flip-flops. So at least in this class, right? That's plenty really to hold to design all the finite state machines we're going to design in this class. So at least in this case with one chip, now I can hold 4 state bits. That's looking pretty good. If I'm trying to implement either of these combinational logic bubbles. What we've already seen is that if instead of using discrete gates, I can use a multiplexer, right, to implement this logic as well. So with the 74151, I can implement an expression with 3 variables or fewer. If I'm going to use the 74150, then I can. This is a 16-to-1 multiplexer, so I can implement an expression with 4 variables or less. And that's definitely probably a little easier than building the actual circuit. But even still, as my finite state machine gets larger, even for many of the finite state machines we've seen in this class, this might not be sufficient, right? If I have, for every one of my output bits, right, I need at least one of these. If my current state has more than 4 bits, 5 or 6 bits, then I'm kind of screwed. Over here, the combinational logic gets even tougher if I'm needing to include my inputs. So ideally, we'd have a solution that's a little more powerful, and so we're going to take a look at that now. What if we need more? What if we need more? We need to express larger Boolean expressions in logic. So what I'll want you to think about now is the fact that these multiplexers that we're using to implement like 3 and 4 variable logic, right? We could almost consider that like a very small form of read-only memory. The fact that you can see here in the diagram in the middle, when I'm setting the inputs of my multiplexer to a 1s and 0s, I'm almost like hard coding these 1s and 0s into this device that I could think of as a memory, where the select lines to my multiplexer are sort of the addresses of the data that I want to retrieve from this device. And so my 74151, I can almost consider it to be like an 8-row read-only memory device that in each row stores a single bit of data. And I could actually extrapolate that even further, right? So if I have any size memory device, I could imagine that the address lines are the inputs to my combinational logic, and the data that lives at those memory addresses are the output values from that combinational logic block. So generalized, right? Like if I have memory that has 2 to the 16th memory spaces, then I have 16 address lines that could potentially be 16 different inputs to this combinational logic block. If each of those memory locations stores 8 bits of data, right? 8 bits come out, then I can use 16 inputs to compute eight different outputs. although it's definitely a little more expensive than a normal kind of 7400 integrated circuit. Clearly, it's much more capable. And so the one we're going to look at or we're going to use in the lab is the AT28. This is an 8 kilobyte EEPROM, right? So there's this actually has 13 address lines, so 13 inputs to my combinational logic and 8 outputs. And so you can imagine this memory system, right? Like it's almost like a big table where I've got 8,000 rows, excuse me, and at each row is a byte or 8 bits of data that I can store there. And so you can see down here what I'm using this memory system for is to basically start to implement the actually the state table from the last lesson, right? We saw here that when I took my state diagram, I sort of wrote out this state table. I'm inputting my current state and my input values, so these first 4 columns, and I'm using those values to determine my next state and my heater, the last 2 columns. So it's almost like these first 4 columns are like the addresses that I'm trying to retrieve a piece of data from, and that piece of data I'm retrieving are the next state and the output bits. So let's go back to this little diagram right here. To be able to use the AT28, what I'm going to do is rearrange this diagram up here just slightly so that there's just a single combinational logic block. All right. This combinational logic block is going to look at the current state and our inputs, and then from those two, it's going to compute the next state and the outputs. And what this does is it allows me to sort of insert my AT28, right, my EEPROM for this big combinational logic bubble. And we'll assume that I want to, I'm going to use a 74175 to hold my state bit. So I've got a 74175 right here to hold my state. And so now this is two chips is all, 2 integrated circuits, right? I can store, S here is the number of state bits. I can store up to 4 state bits using my 74175. The AT28 has 13 address lines. Up to 4 of them can be state bits. So, the number of state bits, I could have, 9 or even more different inputs to my combinational logic block to my finite state machine. And since the AT28 produces 8 bits of output, then I can have, my next state is somewhere, 1 to 4 bits, and that plus my output bits can go up to 8. So with these 2 integrated circuits, right, I can start to build some really large finite state machines. So here's how this will look kind of in simulation. And basically you'll build this in the lab. So again, this is the same finite state machine from our last lesson. Okay. And again, I'm going to treat my my current state and my inputs as like the addresses into this memory system. So I'll show you here. This was sort of the little table that I was working with. These 4 columns here became Q, bar, cancel, and timer. And so when they are all 0, then my outputs were right here. Q prime and heater were both 0s. I'll jump to kind of a more interesting one here, right? In this row, 0, 1, 0, 0, my outputs are 1, 0. So I'm in if I go to the row 0, 1, 0, 0, my outputs are 1, 0. So I'm using, this Excel sheet is directly taken from this state table here. And then it's also copied directly into this ROM device. So you can see here across this little top row are the those values that are in my data that are basically telling me what my next state Q prime is and also what my output is going to be. And if I start running this, so I'll turn on my clock. You can see I'm hanging out here in the state 0, which was the wait state. Nothing happens if I press my cancel button. Nothing happens if I press my timer button. But as soon as I press my bar, right, I'm pushing down the bar on the toaster, then I went into my state here where I'm starting to toast my device. If I press the bar again, nothing's happening. But as soon as I press either the cancel button, or if I were to go back into this state, I were to press the timer were to expire, that I would return to my 0 state. And so this read-only memory device right here, which is we're going to use the AT28 in the lab. I'm using to implement both my next state logic and my output logic. And the cool part about this is now with for a couple of dollars, $5-10, and 2 integrated circuits, I can build some very large finite state machines. All right, that's all I got, folks. I'll see you next time.